So my name is Nurhuda Kisina binti Muhammad Azwan. ID matrix 1221708. 3.
Hello, my name is Muhammad Maziki Sharman. My matrix number 1232140. Ciao.
Okay, my name is Aidin Azri bin Kamal Zaman. My matric number 1233294.
The objective of this lab is to describe the kinematic model of a differential drive mobile robot, to understand the operation of open loop control using MATLAB Simulink, to observe the effect of input variation of robot movement and settling time, and to analyze the robot response in reaching the desired position. Next, we go to a description of the robot parameters. The robot used in this experiment is the PIONER 3DX, which is a differential drive mobile robot or DDMR. The robot movement in this part A is described using 3 main parameters, which are X position, Y position, and orientation angle phi. The X and Y parameter represent the robot location on the coordinate plane, while phi represent the robot heading direction or rotation angle. In this experiment, the initial condition was set to X equal to 0, Y equal to 0, and phi equal to 0. The robot movement was controlled by changing the input value U to reach the desired final position and observing the response using the output graph. Then we go to the tool used, including their advantage and disadvantage. For this experiment, we use MATLAB Simulink to simulate and analyze the movement of the PIONER 3DX differential drive mobile robot under open loop and closed loop control. Simulink allows us to build and test the robot model without using physical hardware. The advantage of MATLAB Simulink are it provides an easy graphical interface, allow fast simulation, and help visualize robot movement and output response accurately. However, the disadvantage are that simulation result may differ from a real robot behavior because real environment contain disturbance and uncertainties. It also requires computer resources and understanding of the software operation. Now, before we go to the procedure of part A, first we need to download the MATLAB Simulink file and open it at the MATLAB software. After we download the file, we will try run this MATLAB Simulink file, and the MATLAB Simulink model for open loop control was open with the initial robot condition, which are set at X equal to 0, Y equal to 0, and orientation angle equal to 0. So the output scope was observed and the graph were recorded for analysis. Next, we are going to select 2 additional desired final position, which we need to change the value of X. So the X value I choose is 2, 5, and -3. And for the Y, all the value is 0. I will explain how the robot will move to reach each desired position. So the first position is initial condition, which are X equal to 0, Y equal to 0, and angle equal to 0. And next, we want to go to our desired position, which are X equal to 2, by changing a step time equal to 4 seconds and initial value equal to 0.5. So the next position is 500. So we need to change a step time equal to 5 and initial value equal to 1.0. Okay, here this graph of the X equal to 5 position. And lastly, we want to go to -300 desired position by changing step time still equal to 5 seconds, but initial value we change it to -0.6. And we see the graph show we successfully get our desired position. Based on the result obtained in the part A, it can be observed that the robot successfully reached all desired position by adjust the input value. For example, the position of 2 meter the robot reached the target faster with a settling time of 4 seconds using U equal to 0.5, and when the desired position increased to 5 meter, a larger input value of U1 was required and settling time increased to 5 seconds. For the negative position of negative 3 meter, negative input value U negative 0.6 was applied to move the robot in the opposite direction. Overall, the results show that the open loop control depends completely on predefined input value and does not use feedback to correct error during movement. Therefore, changing the desired position requires many adjustments of the control input.
So first we need to open the MATLAB software, and then open the file from the link using MATLAB. So we need to open this one. Okay. And then okay, here's the file. So the next step is we need to rearrange the block diagram. So first we need to put the desired block at the first place. Okay, this one, and controller like here, and the robot right here. So and then we need to connect all the block diagram. So EX we connect to the EX, UI we can EY we connect to EY, EXB we connect to PIDW, EYB PIDW, and then U go to U, W go to W. This is the connections of the this part closed loop control. So and then we need to state the controller parameter for PIDU based on table 2, which is for this time the parameter we use is 0.5 for PIDU, and then for PIDW is also 0.5. For the desired position is 2 and 0, and then after that we need to observe the output. We need to click on the output string ni, and but we need to play first. Tekan button play, click button play, and then turn playing. Wait like this. Okay, and then we can see the output graph. Oh yeah, this is the output controller parameter. We need to adjust the desired value to perform the next step. So this time I choose 2 for desired X value, and for desired Y value. So you can see the output. And this is the output. We need to play. Yeah. For the discussions of the result of part B, for the case 1, when the desired position X equal to 2 and Y equal to 0, and the controller parameter value is 0.5, the output graph show that the X position increased smoothly while the Y position and orientation remain constant. No oscillation was observed. This indicates the stable tracking performance. According to a study, lower proportional gains produce smoother control action and improve system stability. For case 2, when controller parameter equals to 1, the robot continued to show a stable response with a similar output trend. The X position increased steadily while the Y position and orientation remained unchanged. This suggested that the controller was able to correct the tracking error effectively while maintaining stability. For case 3, when the controller parameter equals to 12, the response remains stable with no noticeable oscillation Although higher proportional gains normally increase responsiveness, the ideal simulation model maintains stable behavior throughout the experiment. So next, for the case 4, when the desired position of x equal to 2 and y equal to 4, the controller parameter value for KPU and KPW is 0.5. The output graph show that oscillation appeared in both the x and y response, while the orientation angle continuously increased. This occurred because the robot needed to control both its position and heading simultaneously. The low gain value resulted in slower error correction. For the case 5, when the controller parameter equals to 1, the oscillation amplitude becomes smaller compared to the previous case. This indicates improved tracking performance as the controller responds more effectively to the position error.
Okay, here is part C. Okay, in session I'm going to improve the steady state error performance in part B. So using the same position as in table 2, I will run the Lab simulation file. So for desired positions, I setting 2 and 0 first. Then here I set up proportional 1, integral 0 and derivative 0 as the mentioned on the table 3. Also same for PIDW 100. So apply and OK. Then I press the button run. Then we can see the output. Okay, so for number 2, I set this desired position 2 and 4. So for controller PIDU, I set 1 0.2 and 0.5. So for controller, the same 100. And here is the output.